and welcome to this Design Online webinar from Eureka in association with Maxon. My name is Paul Fanning and I'm the editor of Eureka. Today's presentation is entitled Choosing Drive Systems for Lab Automation and will be presented by Matthew Dean, Medical Sales Engineer for Maxon. But before I hand over to Matt, I'd just like to remind you that if you have any questions during the presentation, please type them into the box on the right-hand side of your screen, and hopefully we'll be able to answer them. If we're not able to answer them today, we will be handing them over to Maxon and they will answer them for you offline. And it just remains for me now to hand over to Matt. Over to you, Matt.
Thank you, Paul, and welcome to this webinar about drive systems for lab automation. As Paul said, I'm Matthew Dean, Medical Sales Engineer for Maxon UK and Ireland. So, good place to start is I'll tell you a little bit about Maxon. So what you're looking at there is a picture of a nice Swiss lake, and on the right-hand side you can see the Maxon factory. A few facts and figures about Maxon. Maxon's been making motors since the early 60s, based geographically in the middle of Switzerland, and we have over 3,000 employees worldwide. Typically in a year we make over 5 million motors and 16,000 different variants. We have all the motor competencies you would expect us to have: winding technology, gearbox engineering, sensors or encoder development, electronics, and system integration. So that's just a little bit about Maxon. So let's just have a quick look at the history of lab automation. So where did it all start? It started in the late 50s, where someone had a great idea to invent a machine called an auto analyzer. CFA stands for continuous flow analysis. And what this machine did was it took a fluid and it broke it up into smaller pockets of fluid by using air. So if you imagine a pipe, you'd have a little pocket of fluid and then a pocket of air behind it, then another pocket of fluid, and then each pocket of fluid would flow through the analyzer machine. What this machine did was it took out the need of lots of people to separate the liquid into smaller parts to analyze it, and it greatly increased the flow of the process. So that was the start in the late 50s. Then if we go to the 80s, the gentleman you're looking at there is Mr. Sasaki. He's an interesting gentleman, and in the early 60s, he worked at the Hiroshima Research Institute for victims, and he was exposed to American type processes which were looking at automation, and he put together the idea of automating a lab. So TLA, Total Lab Automation. The father of that is Mr. Sasaki. So within a lab, there's three basic levels of automation. First of all, manual. So this is people doing single step operations, one by one, doing it all by hand. It's very flexible. You can change the process quite easily, but it is totally manual. The next level, standalone apparatus. So you have machines which are dedicated to a process, but the machine could be fed by a human or a robot and unloaded at the other end, again by a human or a robot. So the process is automated, but the automated machine is dedicated to one task. Then the final level, total lab automation. So this is a lab environment where people are very rare, and the process is handled totally by automated processes. So a dedicated machine would do a process, and the output from that machine would be the input into another machine. So out of this automated lab, you would get what you wanted. Hot topic of the day is vaccine. The vaccine is made in this type of environment, total lab automation. So why would you want to automate a lab? Humans are very flexible and very dexterous, but we are all flawed. And humans are flawed because we're not very good at doing repeatable tasks without mistakes. And also, humans can contaminate the lab. We're all used to seeing people dressed up in lab coats and hats and gloves, etc. When you have machines in there, you can sterilize it, and yeah, human entry can be avoided. And also, if you automate the process, machines can do tasks quicker than humans. So you lose the flexibility, but you gain in speed. So the throughput from an automated lab can be much higher than a manual lab. So if you're automating a lab, what are the key challenges? There's three words in there, bold in red: reliability, throughput, and reproducibility. What I want to do is, if you look at the pie chart to the right, what you'll see is that this makes a profound statement, and this was a recent survey. Nearly 1,600 researchers were surveyed, and just over half of them said that there was a significant crisis in reproducibility. What that means is that you set up a process within the lab, and what you get out of it on day one, and if you compare that to what you get out of it on day two, might not be the same, which is a major problem. Throughput and reliability, obviously you get when you automate something. As I said on the previous slide, you can get machines to do repeatable tasks quicker than humans. And reliability, well, the robot always turns up for work and he doesn't go on holiday. So those are the challenges, but the key one there is reproducibility. So with those three topics in mind, when it comes to picking a drive system, I'm just going to go down the list. It starts off with throughput. Basically, what you want to do is you want to speed things up. The faster the processes take place, the more output from the lab is possible. In all of these lines on this slide, it will mention the ironless motor. On my coming slides, I'll explain that in more detail. But throughput, a dynamic drive, faster system with an ironless motor, repeatability, the less components. So you're trying to make it reliable. So the less moving parts, precise motor control. Again, the ironless motor helps here. Precise direct drives. What that means is that if the motor is small, you can put it exactly where you want, so you have a lot less power transmission components in the system. High resolution encoder, what that does is it tells the electronics exactly where things are. Reliability, again, that comes from high quality drives. The thousandth drive off the line, the performance of it will be very close to the first one off the line. The last topic there is efficiency and power density. Power density, what that means is that you get the most amount of power out of a given size. In the real world, what that means is that you can use maybe a smaller motor and gearbox and put it closer to where you want it if the power density is high. Efficiency, again, electrical efficiency is important. You have less heat losses within the lab, and also the cost of running the lab will be lower. So I'm going to come now to the ironless winding and what I mean by that. So the key component on this slide is identified as, look for part number 5. That's the copper cylinder. That is the winding within the motor, and the winding is not wound around iron laminations. That's why it's called an ironless winding. So that part with the copper cylinder or the winding, that's the only part that moves within the motor. It runs on the shaft, which is supported in bearings, and because you've taken the iron out of the winding, i.e. the copper wire isn't wrapped around the iron laminations, it means that the rotor inside the motor, the bit that moves, is very light. It has very low inertia and is very dynamic. So when you ask the motor to do something, you don't have to wait a huge amount of time for it to accelerate and decelerate. It very quickly does what it's told to do, which when you're automating a process is absolutely vital. The other benefit, if you take with the ironless winding, is if you look at components identified as number 2, which is in the heart of the motor body, that is the magnet. And the traditional way of making a motor is to wind the copper around iron laminations and put the magnet around the outside of the motor. When you take the iron out and you have a winding like item number 5 here, you're able to put the magnet in the heart of the motor. And what that does is it means that all the power from the magnet goes through the winding. And what that equates to is torque. And if you have a higher level of torque from the motor, the power density is increased. So that's, if you take one thing from this presentation, I want you to take what the ironless winding does for you. So this is again an ironless winding, but in a brushless motor. The previous slide was a brushed motor. This is brushless. And again, if you look at component number 4 there, which is the copper cylinder, that is the winding. That is put inside the motor body. What rotates within that is the rotor with the motor shaft. That's item number 5 and 6. And the magnet runs inside the ironless winding. Now, what's important with this is that because the winding isn't wrapped around around iron, you don't have any cogging torque from this motor, the same as the brush motor. You have a continuous 360 degree of magnetic field, so the motor is free to turn through 360 degrees. So if you want precise control and the motor to stop where you want it to stop and not fight against the internal detent or cogging torque within the motor, then the ironless winding does that for you. So high power with a small footprint. Really, this is talking about power density. This is just an example of an 8mm diameter motor and gearbox. The motor is a 4-pole motor. What that means is the magnetic return within the motor body, that is the part between the copper section and the wall of the motor, can be thinner. And if you make that part thinner, you can make the rotor bigger. What that does for you is it gives you more torque. So again, a high power density. So a typical package, which is 8mm like that, 50 milliNewton meters of torque coming out the gearbox, and up to 75% efficiency. Again, Maxon has developed special bearings for use with inside that gearbox to increase both the torque capability and the efficiency. So why is all that important regarding motors? Well, within a lab, an automated lab, often the motor would be bolted to a pump to move fluid around the lab. Whenever we switch the telly on, you see the COVID vaccine. It's a liquid inside a little glass vial. Those vials are handled through total lab automation. So they're filled and capped with automated processes. Now, if you take a vial and you want to fill it with the vaccine, you need to precisely dose the fluid into the vial. You don't want a little bit too much, and you don't want a little bit too less. And it needs to be done at high speed. So you're looking for precise control of a pump, multiple pumps, so multi-axis, and they could all be working in sync. High power density from the motor. You don't want giant motors trying to turn the pump. You want the smallest motor possible, and you want the motor and the pump to be highly dynamic. Now, just as an example, if you imagine we added 1 second to the filling time of each vial, and there's hundreds of millions of vials, very quickly you'll see that the delays in producing vaccine would become massive. So having a dynamic lab system handling the vaccine is part of the way as how these companies have made vaccine in vast numbers and quickly. This slide here just gives you an example of a pump that Maxon worked closely with a company called CSEM, designed this little pump, and what this pump does, linear flow, you've got very precise control of the fluid. The way the pump works is that you have discs running in grooves, and the fluid goes into the grooves and the disc moves the fluid around the pump. It's pulsation free and easy to scale. The pump that you're looking at there, the motor and pump, the motor there is 6 mm in diameter. I think the body of the pump is probably 12 mm, but it can be scaled up and can be scaled down. The key message from this slide really is that the motor and the pump within fluid handling inside the lab are very, very closely linked, which is why Maxon works with pump companies. So pipetting, we've all seen on telly people holding a pipette where they're filling up the sample trays. They press a button and the machine will pick up a small quantity of fluid and dose it into the sample trays. If it's a handheld device, there's a couple of things that you want. Firstly, you want it to be dynamic. When you want to pick the fluid up and you ask it to do it, you want it to do it instantly. You don't want to wait. Again, it comes back to the ironless winding and a dynamic motor. Long battery life, so it's handheld. An efficient motor equates to long battery life, and who doesn't want their batteries to last longer? And also we're able to offer the full package. So within a pipette, there'd be a motor, gearbox, encoder, and also something to give you the linear motion, ball screw, lead screw, that type of thing, and electronics. So all that goes together to make the system within the pipette. So this application here, decapping, it doesn't sound very glamorous, but it is vital. Essentially, putting caps on and off vials. What's important here is that you want the part or the mechanism that decaps or puts the cap on as close to where all the vials or sample bottles are. You don't want a big machine that takes time to go off to do it and then come back. You want the part that screws on and off the caps to be as small as possible and as close to the action. And yeah, using the 8 mm motor and gearbox and the electronics enables you to do that. So keywords here, high power density, long lifetime using a brushless motor, 10,000 hours plus is achievable. And yeah, Maxon would supply the whole system. So someone once said, power is nothing without control. What's actually controlling controlling these motors, which are driving pumps, etc.? And the answer is that there's various sensors that you fit, that Maxon makes and fits to the backs of motors to tell the electronics exactly what the motor rotor is doing. So encoders come in two distinct sort of families. One would be a relative encoder, and the other type would be absolute. The absolute encoder has a couple of advantages in that it always knows where it is. So if it loses power for whatever reason, when you switch it back on, it will remember where it last was. Whereas a relative encoder is simpler, but for many applications is more than enough to tell the electronics what you want. The resolution of the encoder is important. The higher the resolution, the more pieces of information the drive system has to tell it where the rotor is, the motor rotor. which for some applications is vital. So it's by using encoders that enables you to precisely control the lab, the automation process, or an individual axis. So here's a nice picture of typical Maxon type products. All of these products could be used in relevant to lab automation, whether it's catalog, motors, gearboxes, encoders, etc., or customized in some way. Most people want a customized product in some form or another. It could be special bearings, special shaft, special leads, connector, etc. But at the heart, it's a catalog. It's based on a catalog product. Or the last section there, fully customized product. So that's a product dedicated to do one specific application, designed. You start on a blank sheet of paper, and you develop a product specifically for one application. And that is the end of my webinar.
Thank you very much, Matthew. That was great. Question for you that we have here is what are the future challenges for lab automation?
Well, the big challenge that people are faced right now comes back to the vaccine, and that is that the world is going to need the vaccine. And the way that has to be met is you can't just use the existing automated lab systems that we have to churn out vaccine and then ship the vaccine around the world. What each country is going to want is their own automated lab process or system set up, so countries are making their own vaccines, not relying on a couple of countries to ship them vaccines as and when. So that is the big challenge. So that means far more lab automation needed around the world right now.
Okay, thank you very much. Very, very topical, of course. That's all we have time for today. But as I said earlier on, if there are any other questions that we haven't had time to ask, we will be handing those on to Maxon and they will answer them for you offline. With that, it just remains for me to thank everybody for joining us today and to thank Matthew. Thank you very much.